In Chapter 6, we showed that the work done on an object by a net external force was equal to the change in the object's kinetic energy. The work-energy theorem led directly to the principle of conservation of mechanical energy. Now we want to show that the impulse-momentum theorem also leads to a conservation principle, known as the conservation of linear momentum. Let's look at the simple case of two objects of mass m1 and m2 colliding with each other. Before the objects collide, they have initial velocities v initial 1 and v initial 2, and after they collide, they have final velocities v final 1 and v final 2. Because of the forces acting on each object during the collision, the initial and final velocities are not the same. Before proceeding, we need to distinguish the two types of forces that can act on the objects. The first is internal forces, which are forces the objects within the system exert on each other, and the second type is external forces, which are forces exerted on the objects by agents external to the system. During the collision, a force is exerted on object 1 by object 2, called F12, or the force on 1 from 2. Likewise, object 2 exerts a force on object 1, called F21, or the force on 2 from 1. These two forces constitute an action-reaction pair in accordance with Newton's third law. Therefore, F12 is equal to minus F21. These are internal forces, since they are forces the objects in the system exert on each other. There could, in principle, be external forces too that act on the objects. Weight due to gravity, friction, and air resistance, for example, would be external forces. The total force on each object would then be the sum of the internal and external forces. We can apply the impulse-momentum theorem to each object to show that the impulse provided by the total force acting on the object is equal to the change in the object's momentum. Here, the total force is the sum of the external forces plus the internal force F12 or F21. We write this out for both object 1 and 2. Now, if we add these two equations together, we get a result for the system as a whole. The left side of this result is equivalent to the sum of the total external and internal forces on the system, and the right side is equal to the difference in the total final momentum of the system and the total initial momentum of the system. We represent the total momentum of the system with an uppercase P. Notice on the left side that the sum of the average internal forces is just equal to F12 plus F21. However, by Newton's third law, we know that F12 is equal to minus F21. Therefore, the sum of the internal forces is 0. The cancellation of the internal forces occurs no matter how many objects we have in the system. Now our equation is reduced even further, and it only depends on the sum of the average external forces. Let's now suppose our system is isolated. In an isolated system, the sum of the average external forces is equal to 0. Therefore, the left side of our equation is 0, which means the right side must also be 0, or equivalently, the total final momentum of the system must be equal to the total initial momentum of the system. This result is known as the principle of conservation of linear momentum. In words, it's stated as the following: the total linear momentum of an isolated system remains constant, or conserved. An isolated system is one for which the vector sum of the average external forces acting on the system is 0. In the absence of external forces, the total momentum of the system is conserved, regardless of the number of objects in the system. For our two-object example of colliding masses, the conservation law of linear momentum would result in the following equation, where the total final momentum is the sum of the final momentums of each object, and the total initial momentum is the sum of the initial momentums of each object. Knowing 3 of the quantities in this last equation allows us to solve for an unknown fourth quantity. As an example of how we can apply the principle of conservation of linear momentum, consider the following situation, where two boxcars are moving in the same direction along a straight section of track at different but constant velocities. The boxcars have masses of m1 and m2 and initial velocities of v initial 1 and v initial 2. Boxcar 2 overtakes boxcar 1 and couples to it. What is the final velocity of the two cars immediately after they become coupled? Neglect friction. The two boxcars constitute our system, and the sum of the external forces is equal to 0 since we are neglecting friction and the weight of each car is balanced by the normal force from the track. Thus, the system is isolated. Therefore, the total momentum before the cars collide has to be equal to the total momentum after the cars collide. Since the two cars are coupled after the collision, v final 1 will be equal to v final 2, and we just call it v final. We can now solve this expression for the final velocity of the two cars.